Thank you, Luis, for the invitation. I don't consider myself an expert, but certainly the talk is going to be in about orthogonal polynomials in the complex plane. This talk is based on a paper together with Aaron Bergman, who is now a professor in Leuven. So let me see. Okay, okay. So so we are going to consider here orthogonal polynomials, but not in the classical sense of orthogonality on the real line or say on the unit circle, right? So these are going to be orthogonal polynomials with respect to area measure, right? So two-dimensional Lebesgue measure. And so what we're going to do is we are going to consider D here is a bounded domain in the complex plane, as you can see here in the figure. And it's a domain whose boundary is a piecewise analytic Jordan curve. So it's a Jordan curve, but made out of finitely many analytic arcs. And dA, here A for area, right? So dA is going to be the normalized area measure, normalized in the sense that it's divided by pi just for the sake of getting some slightly nicer results. When you write the formulas, if you normalize the area measure, the formulas are going to be a little bit nicer. So this is our setting, right? So D is a bounded domain whose boundary is a piecewise analytic Jordan curve. And then Pn here is the sequence of orthonormal polynomials with respect to this normalized area measure over that domain. So they are going to be polynomials satisfying that the integral of Pn against the conjugate of Pm over that D with respect to the normalized area measure is equal to 0 if the polynomials are different, and it's going to be equal to 1 if they are the same. So they are polynomials of a complex variable. Okay? And what we are interested in here is in understanding the asymptotic behavior of these polynomials and the asymptotic behavior also of the zeros of the polynomials, of the orthonormal polynomials, as the degree approaches infinity. Now, you all who have worked in orthogonal polynomials are very familiar with the concept of normalized zero-counting measures associated to the polynomials. So it's the measure that places a mass point at each zero of the polynomial, counting multiplicities, and you divide it by the degree of the polynomial, right? So it's the average of these mass points at the zeros of the polynomials. And by the way, if you can interrupt me at any time with any questions, right? And so we're going to write that the normalized zero-counting measures converges to a measure mu in the sense of weak convergence of measures, right? So the meaning of this is that if you take a compactly supported continuous function, f, and you integrate this continuous function with respect to these normalized counting measures, that integral is simply going to be the average of the values of the function at the zeros of the polynomials, right? Then as the degree goes to infinity, this average converges to the integral of f with respect to the measure mu. So if that happens, we write this convergence like that. Okay, so what is known, or what was known in this context, right? So the main result before our work is a result by Stylianopoulos from 2013, where he proved that if the boundary of the domain D has no cusps, Now, a cos means that either the interior angle or the exterior angle, one of the two is 0, right? So if that doesn't happen, then you have what is called a strong type of asymptotic formula. So if you divide the orthonormal polynomial by the nth power of a function phi times the square root of n plus 1, so that quotient converges to the derivative of this function phi uniformly on closed subset of the exterior of the boundary. So let's say for z outside the closure of the domain, right? So now, what is this function phi? So this function phi is the so-called canonical conformal map that sends the exterior of the boundary onto the exterior of the unit circle. So the standard normalization is that this map sends infinity to infinity, and the so-called derivative at infinity is positive. But so for all of you who are not very familiar with this setting, this is going to be the important function for us here, this phi. And again, this is the conformal map that takes the exterior of the boundary of D, so the exterior of this curve, onto the exterior of the unit circle. And there are infinitely many such maps, but the ones that we want is the one that takes infinity to infinity. So we have this strong type of asymptotic formula for these orthonormal polynomials with respect to area measure over D. So one conclusion is that that if you think of the zeros of these polynomials asymptotically, so as the degree goes to infinity, these zeros have to accumulate on the closure of D. So if you were to picture these zeros, they essentially will accumulate on the closure of this domain D, so on D and its boundary, right? So where exactly we are going to see, right? But that's something that follows from this asymptotic formula. Okay, so now I have to define what a corner of this piecewise analytic curve being reflection invariant means, what that means, right? And I'm gonna do it in a unprecise way in some way, right? But because the precise definition would be a little bit too heavy. But so essentially, let's say that this is a corner of my piecewise analytic curve, right? So near that corner is made out of these two arcs. One is blue, the other one is red. Okay, and they are so-called analytic arcs. So there is this concept of reflection of an analytic arc, or across an analytic arc, right? It's called Schwarz reflection. But okay, so let's say you take this arc, the blue arc, and there is a way to reflect it about the red arc. So this blue arc is going to give you a new arc here, and this reflection is going to give this new arc is also going to be analytic, and this reflection also preserves the angle, right? So whatever the angle between these two arcs was, then the angle between the red and the new blue arc is going to be the same. Okay, so now you can reflect the red arc across the new blue arc, and then you create a new red arc, right? And then you can continue like this. So there are two possibilities. Maybe you return to the original arc after a not number of reflections, or maybe you don't. But if you return to the original arc, this is what then these properties, we call it reflection invariance for that corner. Because after a number of reflections, you come back to the original arc. Now, this property, right? So that if every corner of the curve, right, is reflection invariant, that is equivalent to saying that a conformal map of the interior of the interior D onto the unit disk has no singularities on the boundary. So there is this characterization between reflection invariance and the possibility of a conformal map of the interior of the domain onto the unit disk having no singularities. But okay, that's not essential to our discussion here at the moment. Okay, so there is this result from Levin, Saf, and Styrianopoulos from 2003, where they proved that if the boundary of the domain, so if the piecewise analytic curve, right, has at least one non-reflection invariant corner, right? So let's say a bad corner. But if it has at least one bad corner, one that is not reflection invariant, that is equivalent to saying that the normalized counting zero measures converge to the so-called equilibrium measure of the curve, at least through some subsequent. So it's an if and only if condition, right? So having a bad corner is equivalent to saying that through some subsequence, the normalized zero counting measures converges to the equilibrium measure of the curve. Now, what is this equilibrium measure? Well, this comes from potential theory, but at least in this situation, you can define it through the derivative of that exterior conformal map. So it's a absolutely continuous measure, so absolutely continuous with respect to the arc length measure on the curve, and the derivative is just the absolute value of phi prime. But okay, so what is important to us is that the support of this equilibrium measure is the whole boundary of T, so the whole curve. And therefore, in this situation, you know that every point of that boundary curve is going to attract zeros of the polynomials as n goes to infinity. So that follows from this weak convergence of the normalized zero counting measures. Okay, so I will give you some examples, right? So, for instance, if you take the case of the domain being a regular n-gon with n sides, n being greater than or equal to 5, right? So 5 or more sides. All of these sides are the same length. So this is in this situation, all of these corners are going to be bad corners. And you can see this picture here where we have plotted the zeros of these polynomials from degree, say, 1 to 130. And you can see how these zeros are being, most of them, right, attracted to the boundary. And a few of them can stay inside, but the bulk of them is being attracted toward the boundary. And that's essentially what's going to happen every time you have a bad corner. So what we are interested in is in the situation where all of the corners are good. So all of the corners have this reflection invariant property. So, and that's what we're going to assume from this point onward, right? That every single corner, which I denote by Z1 up to ZQ, of the boundary of the domain, right, of this piecewise analytic boundary, is reflection invariant. Now, if that happens, then the interior angles at each corner, right? So, for instance, here I have Z1, Z2, Z3, and Z4 corners, right? In this case, so every time that happens, the interior angle formed by the arcs at every corner has to have a very special form. It has to be of the form pi over some natural number greater than or equal to 2. So this is a necessary condition. It's not sufficient for reflection invariance, but if you know for sure that all the corners have this reflection invariance property, then the interior angles have this particular form. And I will show you some plot of zeros of these Bergman polynomials or orthogonal polynomials with respect to area measure in situations where the boundary, as I am assuming, right, all the corners are good corners. So I already mentioned what happened in the case of regular n-gons for n greater than or equal to 5. There are only 2 n-gons that have good corners, which are the first two, right? The one with 3 vertices, which is the regular equilateral triangle, and the square. If you plot the zeros of these polynomials, you will see that they are no longer going toward the boundary. On the contrary, they actually stay on these segments connecting the center to the vertices, right? In both cases, both situations. So in the case of the triangle and in the case of the square. And in fact, this was proven by Saf and Maimescu in 2003. So they proved that actually the zeros lie exactly on those segments. And in the limit, they are going to sort of fill out the segments. So every point of those segments is going to attract zeros of the polynomials. So something drastically different is happening here, right? So I will show you now other case, right? So now, for instance, if you take the domain who is bounded by 2 arcs of a circle, so they are circular arcs meeting at pi over 4. Then if it was also proved by these authors, like Saf, Levin, and Stylianopoulos, that the zeros actually lie on the segment connecting the 2 vertices. If you take, for instance, half of the unit disk, right? So then where are the zeros of the Bergman orthogonal polynomials for half the disk? Well, they appear to accumulate on some arc joining the 2 vertices in this case. And one more example, if you look at the so-called Bernoulli-Leibniz case, Bernoulli-Leibniz case is a curve that looks like an infinity sign, right? If you look at half of it, that curve is going to look like this, and it's going to have only one corner, which is a very interesting case because you only have one corner here. So what happens? Well, the zeros are going to actually lie on the segment that joins the single corner with some point inside. This point actually in this case is 1. Okay, so then here is our theorem, what we were able to prove, right? That in general, if you have a domain that is bounded by a piecewise analytic curve, whose corners are all reflection-invariant corners, then in that situation, there exists a compact set S inside the domain. So here is, you should look at these pictures to understand essentially what's going on. So this is my original domain D, right? In this case, it has 3 corners only. So there exists this compact set S. In this case, it's made out of these 3 segments and some sort of triangular set here, right? So as you can tell, this set is fully contained on the closure of D, but indeed, the only point on the boundary that S has are the corners. So it only touches the boundary at the corners. Otherwise, it's fully contained inside the domain of orthogonality D. So both the set S and the complement of it are connected sets. And that exterior conformal map that was defined outside the curve, the original curve, actually has a conformal extension to the complement of the set S. So all the way up to the set S. And that strong asymptotic formula, originally proven by Stylianopoulos outside the boundary, is actually holding outside this smaller set S. So it carries over. So the strong asymptotic formula carries over from the exterior, so from outside this curve toward inside, right, outside this set S. So we were able to prove that there exists this minimal set S where we have strong asymptotics up to that set, from all the way coming from infinity up to that set. Okay, what else can we say about this set S? Well, you can also prove that every point of this set S, of the boundary of S, right, of the boundary of S, attracts zeros of the polynomial. So the polynomials are going to, the zeros of the polynomials are going to accumulate toward this set S, and every point of the boundary of S will attract zeros of the polynomials. Outside S, in the limit, there will be no zeros of the polynomials because we have this strong asymptotic formula. And in the case where S has empty interior, then you can prove that there exists a measure mu supported on that, so mu sub S supported on that set S, which is the weak star limit of the normalized zero counting measures at the zeros of the polynomials, right? Okay, so essentially we are able to explain. Okay, so something else. So you see this picture that I drew here for illustrative purposes, right? Well, it's not very far from the truth in general, because what we can, it's not that easy to in general describe what this set S is, right? But you can see here that I've drawn this set S as consisting of some arcs when you are close to the corners. And that in fact is true. So we prove that near each corner, the set S consists of an analytic arc, which happens to be exactly where the boundary limits of this conformal map coincide in absolute value. So for instance, if you take this arc here, right? So we know that the conformal map has an extension all the way from outside to the left side of this arc and also to the right side. When you look at the boundary limit of this conformal map extension in absolute value, they actually coincide on that arc. And this equality, in fact, you can use it as a definition of S near the corner. And you can see, if you restrict the zero counting measures to those arcs, the limiting measure can be expressed in terms of this boundary limit of the derivative of the conformal map. So there is a way to compute precisely on those arcs what the limiting measure is. So essentially, so far this is the best we have been able to say about this set S, right? So we know it's minimal. Near the corners is nice, so it consists of these analytic arcs. Away from the corners, say what happens, so more toward the interior of the domain D, this is more fuzzy, right? Now I will not give you in this talk the definition of this set S because it's a little bit intricate. So if you are really interested in how to define this set S, you would have to consult a paper. So let's go back then to these examples that I showed you earlier, right? So for instance, in the case of a triangle, what is my set S? Well, it's just precisely the three segments that connect the center of the triangle, the equilateral triangle, to the vertices. Similarly, in the case of the square, the set S consists of the two diagonals, right? In the case of the two circular arcs meeting at pi over 2, I think. Yeah, pi over 2 angles. The set S is precisely the segment connecting the two corners. And in this case of half a disk, well, you can define explicitly a certain curve connecting the two vertices, and that's going to be that particular curve is going to be your set S. So these are all examples where the set S actually has empty interior. And so you know that the zeros are going to accumulate exactly on those on that set S. Not only that, you know now that the strong asymptotic formula holds outside the set S. So for instance, in the case of the triangle, you know that there is a strong asymptotic formula outside those three segments, right? So in each of these cases, you have that situation. And also in the case of the half Bernoulli-Leibniz case, what you know is that, and I already told you that it was known that the zeros lie on this segment, but now you also know that there is a strong asymptotic formula holding outside the segment, not only outside the curve, but also that asymptotic formula continues all the way up to outside, say, the segment. Okay, so a sketch of the proof, right? So this is where things could become complicated, because so if what happens with Bergman polynomials, say polynomials orthogonal with respect to area measure on a domain, right? What happens is that what you usually use in the classical setting, right, in the case of orthogonal polynomials, or on the real line or on the unit circle, so you have many tools to deduce results. So for instance, you have recurrence relation, right, in both cases. In the case of the orthogonality over the real line, and on the unit circle, you have these recurrence relations. In many instances, you also have differential equations, right? Plus, the case of the real line as well as the circle, you have strong symmetry. So you have many tools to deduce results about the zeros and about asymptotics. But if you go to the complex plane, now you have any domain, right? And you also have area measure. So you have very limited set of tools. In fact, it's so limited that I've been thinking about this problem for a long time. And only until recently, I was able to find a way to tackle this problem. So you have to see the right way to deduce these results. And typically, it's not going to be an easy argument. So it could be a quite complicated argument. So I'm not going to explain all the details to you. So I'm just going to give you a very light flavor of what is involved, right, in deducing these results. So first of all, we can write that a strong asymptotic formula outside the closure of the domain in this way, right? So you take Pn, you divide it by the square root of n plus 1, you divide it by the derivative of the exterior map and the nth power of the exterior map. And we know that converges to 1. So we're going to write like this quotient minus 1 converges to 0. So that's what we know outside the domain. And this is the result by Stylianopoulos. Now, this not only happens point-wise, or a point outside the closure of the domain, but also uniformly as long as you stay away from the boundary. So the limit is going to be uniformly, but if you stay on some closed set, right? So we know that the strong asymptotic formula already exists outside the boundary curve. So how about then inside the domain, right? Inside the domain of orthogonality. So this is in some way the harder part, right? Because here you have to prove that the orthonormal polynomials, right? The Bergman orthonormal polynomials behave asymptotically as some integral, right? So integral that depends on n. So you see here is the degree n, and so here you have the nth power of that exterior conformal map. The problem with this integral representation is that not only involves the exterior conformal map phi, right, but it also involves this new phi, which is an interior conformal map, one that takes the domain of orthogonality conformally onto the unit disk. So you have an interplay here between two conformal maps, the exterior conformal map phi and the interior conformal map phi. And so you can prove, but this is difficult, right? So, but you can prove that Pn behave asymptotically like this integral times times something that it's very nice, right? Okay, so that's the harder part. Then you have to analyze how this integral behaves as n approaches infinity. Okay, and that's where you're gonna get your set S. And from analyzing this integral, then you get to define the precise definition of the set S, the one that I'm not going to give, right? Okay, so then from that integral representation, you also get that you have a similar limit, right? So, but in the part of the domain that is outside that set S, that minimal set S. Okay, now, of course, you can say, okay, what is this phi function? That was the exterior conformal map, right, originally. But how now here we are dealing with points inside the domain? Well, okay, so you can prove that this exterior conformal map has a conformal extension to the part of D that is not in S, and you still have this limit. Now, this limit, you are proving it for every Z in D and not in S, okay? And it also holds uniformly on closed subset of that D minus S. So what is the situation then, right? So let's say that we now rename this difference, right, the one that we know that goes to 0, as E sub n. So what we have proven is that E sub n goes to 0 as n goes to infinity for Z outside S, right? So let's say S is my set S is consisting of these red arcs, right? So let's say that's my set S. So what we have proven so far is that this En goes to 0 outside that S, but away from the boundary. So we had it outside of the boundary. Now we have it inside of the boundary, but not on S, right? But the problem is that we want to establish this formula that En goes to 0 also on the portion of the boundary that is not a corner, right? Okay, so let's take a point Z0 on the boundary, and let's just zoom in on a neighborhood of that point. So what we want is to show that this limit still holds on that neighborhood. So, okay, so this is a zoom in. So we look at that neighborhood. Then when you go through the proof, you get estimate for this so-called error term, right? So you know that the absolute value of En is bounded by this quotient, the equation of this form. If for points on the boundary, I'm sorry, for points on the neighborhood that are outside, right? So outside the curve, the boundary. So in this white area here. And you have a similar type of estimate for points Z that are in the neighborhood but inside the curve, so on the domain, right? Now, if you look at this estimate, you say, what happens if n goes to infinity? If n goes to infinity, well, you have n here below as well as here, right? So this is going to go to 0. Great. But what happens is that you also have this parenthesis, right? That if Z goes toward the boundary, the absolute value of this conformal map goes to 1. And so you cannot evaluate these quantities at a point on the boundary because it degenerates completely. So it becomes 0 in the bottom. So these error estimates go to 0 like 1 over n as long as you are away from the boundary. If you approach the boundary, as I said, this absolute value of phi of Z minus 1 will go to 0, and so it's going to blow up. Okay, but so essentially what you need is to find a way to glue the two asymptotic formulas, right? So you know that En goes to 0 here. You also know that it goes to 0 here. Unfortunately, the estimates degenerate as you approach the boundary, but still you want to show that En should go to 0 all over that neighborhood, and that's part of the proof as well to prove that is the case. So what we do is that we use an argument similar to the argument at least in the spirit, right? To the argument that you use to prove this Fragment-Lindelof theorem. Is a classical theorem in complex analysis. It's a theorem that allows you to use some version of the maximum modulus principle on a strip. And so by using that type of argument, we are actually able to prove that function En goes to 0 in the whole neighborhood. And in fact, we can prove that it goes to 0 like log of n over n. So we get an estimate on how fast it goes to 0. So the proof consists, if you want, of 3 steps. So the first step is already given. So it's the strong asymptotic outside the curve. The second step is to get asymptotics inside the curve. And then the third portion is to glue these two asymptotics about points on the boundary that are not the corners. Okay, so I think this is my last talk. I mean, my last slide.